Hello, today we are talking about integration by parts. This is a technique that we use for integration, finding an antiderivative, of a product of two terms that isn't a chain rule. So this first example, this is a chain rule example. This is a time we would not use integration by parts, would be find the antiderivative of 2x cosine of x squared. So the inside function is x squared, which means the derivative of the inside would be 2x. So I need to use this 2x because it's the derivative of my inside in order to find my antiderivative. However, in the next example, this is not a chain rule example. This is when I would have to use integration by parts. And so I have two terms. I have a 2x and I'm multiplying a 2x by cosine of x. So that's what makes this a product. So integration by parts. There is a big formula here that you just have to know. So here's my integration by parts formula. The integration of u dv, so u would be one term, dv would be the second term that I'm multiplying together. It's going to be equal to u times v minus the integration of v times du. So that's what we use for integration by parts. So the difficult part in integration by parts is identifying what you want to be your u. I'm going to move my screen. So when I choose u, you're looking for usually the more complicated term out of the two. And I like to use this acronym called ILATE. So if there's an inverse trig within this product, that's the first thing that I would use for my u. If I don't have an inverse trig, but I have a natural log as one of my products, then I would use the natural log as my u. If I don't have a natural log or an inverse trig, but I have an algebraic, like 5x or 3x to the fifth, then I would use that as my u. If I don't have an inverse trig, I don't have a natural log, and I don't have an algebraic, but I have a trig, trig is then going to be my u. And the last one that you choose as your u is your e, which actually means, for example, e to the x. It's actually the exponential. So let's look at example 1. So the first thing that I need to do is I need to select my u. So my two terms that I have 5x and I have e to the 3x. So 5x is algebraic and my e to the 3x is e. So according to ILATE, I want to do algebraic before I do e. So I'm going to use my algebraic as my u. So I've selected my u. My u is going to be 5x. The next thing I need to do is I need to find du, dv, and v. So in my formula for integration by parts, I have my integral is u dv minus is equal to uv minus the integration of v du, which means whatever I choose as my u, the other thing that's left over is my dv. So my u is 5x. That means in this problem, my dv is going to be e to the 3x. So from here, I should be able to find du, and so my du is literally the derivative of 5x, which is just 5 dx. And then the antiderivative of v is going to be, sorry, my v is the antiderivative of dv, and the antiderivative of e to the 3x is e to the 3x. The derivative of my inside is 3, so my antiderivative needs a 1/3. I'm going to deal with my plus c, my constant, at the very end after I've evaluated. So again, I have my formula is integration of u dv is equal to uv minus the integration of v du. So I'm just plugging in what I have. So my initial problem was the integral of 5x e to the 3x times dx is equal to, now I'm going to plug in u, and my u is 5x times my v, which was 1/3 e to the 3x, and I'm going to subtract the antiderivative of my v again, 1/3 e to the 3x, times my du, which is 5 dx. So all I've done so far is I've just plugged into the formula. Now I'm just going to simplify. So what I have is the integral of 5x e to the 3x dx is equal to, and right here I'm going to write that as 5 over 3 x e to the 3x. And then over here I'm going to pull my constants all the way out, minus again 5 over 3 antiderivative of e to the 3x dx. And I should be able to find that antiderivative. So all I have to do now is find the antiderivative of e to the 3x, which I've actually already done earlier. And I'm left with this antiderivative is 5/3 x e to the 3x minus 5/3 times 1/3 e to the 3x. Again, the derivative of the inside is 3, so I need to add a 1/3. And don't forget, we need a plus c because we are finding an antiderivative. And again, we should simplify that 5/3 times 1/3 to a 5/9. Otherwise, that's how you do integration by parts. So let's go to example 2. In this example, it's an example showing that sometimes you get to do integration by parts more than once. So we're starting with the antiderivative of x squared cosine of 4x dx. So the first thing that I need to do is figure out, well, what's my u? And I have two terms, and my two terms are x squared, which is algebraic from isolate the a, and cosine, which is trig from isolate the t. And so the first one I want to use is algebraic, comes before trig. So my u is going to be x squared, which means I now know my dv is the other term I have left over, which is cosine of 4x dx. So I'm going to find my du, and my du is 2x. And my v is the antiderivative of cosine of 4x, which is sine of 4x. And again, the derivative of the inside is 4, so my antiderivative needs a 1/4. And again, I'm going to wait on my plus c until the very end of my integration. So this integral of x squared cosine 4x dx is equal to u times v. So my u is x squared times v, which is 1/4 sine of 4x, minus the antiderivative of v du. V is 1/4 sine 4x, and du is 2x. dx. I apologize, I forgot my dx over here on my u. So from here, I'm going to need to simplify, and notice that when I work this out, I don't know, I still have an integration by parts in this last term over here. That's another integration by parts. Before I start my integration by parts, however, I'm going to simplify. So I still have the antiderivative x squared cosine of 4x dx is equal to, and my first term is 1/4 x squared sine of 4x. And then I'm going to pull my constants out, and that's 2 times the 1/4, so it's minus 1/2 integration. I'm going to put the x in the front, x times sine of 4x dx. So again, I need to choose my u, and I have my x is algebraic and my sine is trig. So my u is algebraic, so my u is going to be x. That means my dv is going to be sine of 4x. So I find my du, and the derivative of x is just 1 dx, and the antiderivative of sine is cosine of 4x. It's actually negative cosine, and then again the derivative of the inside is 4, so I need a 1/4 on the outside. My plus c I will deal with soon. So I need to rewrite this again with my new integration by parts. Antiderivative of x squared cosine 4x dx is equal to 1/4 x squared sine 4x minus 1/2 times u times v. Sorry about that. U times v minus the integration of v du. Not sure why it looks like I'm crying here. I'm not. So I have this now. I now need to make sure I distribute my negative 1/2 and deal with my antiderivative, which I'm going to try and do in this next line because I'm running out of room quickly. Okay, so we have 1/4 x squared sine of 4x. Then I have minus a 1/8 x cosine 4x. And then in here, this ends up being a positive, but the negative on the outside makes this a negative 1/8 integral of cosine 4x. I'm going to actually find the integral of cosine 4x while I'm here. So the antiderivative of cosine 4x ends up being sine of 4x. The derivative of the inside is a 4, so I also need a 1/4, and then I need my plus c. And of course, I should simplify that so that I have a 1/32 in front of my sine of 4x. Otherwise, this is my antiderivative. Moving on to example 3, sometimes you end up with a version of what you started with. So basically what that means is once I start doing my integration by parts, some point along the way, I'm going to get something that looks a lot like this. So we set it up the exact same way. First thing I need to do is pick my u. So my e to the x is obviously an e. My sine is a trig. Trig comes first in ilate, which means my u is going to be sine of x, and my dv is going to be e. So I'm going to have integration of e to the x sine of x dx equals my u is sine of x, my dv is e to the x dx, my du is going to be cosine of x, and my v is going to be e to the x. And I'm going to plug this in. So I have u times v, so sine of x times e to the x minus the integration of v du, which is e to the x times cosine x dx. I keep forgetting my dx on my du's. I apologize. So at this point, what's going to happen is I've got another integration by parts that I'm going to need to do. If you look at what I'm integrating a product, and that needs another integration by parts. So for this one, again, I have an e and I have a t for trig. That's going to be my u is the t. It comes before the e in ilate. So my u is cosine of x, which means my dv is e to the x. So my du is going to be negative sine of x. That says sine of x. I'm not sure why my board's not working. And so my v is going to be e to the x. But my board's really not working. So let's plug that in. Back to what I started with. I started with e to the x sine of x dx. And that is equal to, I'm going to put the e to the x in the front, e to the x times sine of x minus this whole integration by parts. And that is going to be u times v, so cosine of x times e to the x minus the integration of v du, and v is e to the x, and du, again I forgot my dx, is sine of x dx. dx, right there. So at this point, I need to distribute this negative. That's the first thing I really need to do. So I have the antiderivative e to the x sine of x dx is equal to e to the x sine of x minus e to the x cosine of x plus the integration of e to the x sine x dx. Oh shoot. I mean, sorry, above in the line above my du is negative, so this should be a negative sine of x, which means this sign right here needs to actually be a negative. I apologize. So again, my sine of x was a negative. I didn't plug in a negative, I plugged in a positive, making this last term in my second integration by parts a negative. Okay, so again, this example was we were looking for a form of our original antiderivative. So if you look at what we started with, which is this, and you look at this, they're similar. The only difference is one is positive, one is negative. Otherwise, the antiderivative e to the x sine x dx is the same. So we're going to treat that as if it was a variable, let's say a. So as a little side note, this you don't have to do anything. If I had a equals e to the x sine x minus e to the x cosine of x minus a, and I wanted to get a by itself, I would simply do a little bit of algebra. I would add a to both sides, and that would give me 2a is equal to e to the x sine of x minus e to the x cosine of x, and then to get a all the way by itself, I would divide everything by 2. So that would be e to the x sine of x minus e to the x cosine of x all over 2. That's exactly what we are about to do, except instead of the letter a, we have the integral of e to the x times sine of x dx. So we're doing the exact same thing. So I'm going to add to both sides of my equation the integral of e to the x sine of x dx to the right side of the equation and the left side of the equation. And when I do that, on the left side of the equation, I now have two of these things. And once I have two of them, I don't want two of them. I just want one of them, which means I now need to divide both sides by 2. So I have the integral of e to the x sine x dx is going to be this whole thing, e to the x sine x minus e to the x cosine of x, all divided by 2. You could do a half in front of each term. You could do each term divided by 2, whichever way you want to do it. And then I add my plus c at the end because this is an antiderivative. So this is the first half of the video. This is all I expected you to get finished in one night. I'm going to continue with the video though, so the second part you can either do now or come back at 18 minutes a different day and continue the video, whichever you prefer. So we're still talking about integration by parts, but this is an easier method for doing the same process that we've been doing. So we start out with this table that I have at the right side with a U and a DV and a line under it, and I'm simply going to make a table. So step 1, which is right here, I'm going to insert my U. So the first thing I need to decide is what is my U. X squared is algebraic, sine is trigonometric, so the algebraic comes first. My U is x squared. So my U goes under the U column. Step 2, it says enter the dv. That's over here at the right side. So my dv is what I had left over. I'm going to leave off the dx just because it makes things a little more cumbersome and we don't need anything else to add to our cumbersomeness. So that's just going to be the sine of x without the dx. So step 3, take the derivative of the u until you get to 0. So that's literally what I'm going to do. I'm going to take the derivative and put it right below it. So the derivative of x squared is 2x. The derivative of 2x is 2. The derivative of 2 is 0. That's when I'm going to stop. My next step, step 4, I'm going to take the antiderivative until you're even with the last u. So I take the antiderivative of sine of x, and that gives me negative cosine of x. I take the antiderivative of negative cosine of x, and that gives me negative sine of x. I take the antiderivative of negative sine of x, and that gives me cosine of x. And I stop here because I have I'm now even with my last u. I'm like even with the 0. I have the same number of entries in each column. Step 5. Starting with the first u, put a plus, and we're going to do that in front. Then alternate with a negative down all of the u's. So a plus went in front of the first u, a negative goes in front of the next one, a positive goes in front of the next one, and a negative goes in front of the last one. Step 5. Multiply diagonally the first u with the second dv. So I'm going to multiply like this. The first u times the second dv. And I'm going to continue doing that like this. When I get to the last two, I'm going to do the integral of these two multiplied together. So let me write down what I have right now. I have x squared times negative cosine of x. That's negative x squared cosine of x. And then I multiply negative 2x times negative sine of x. So that's plus 2x sine of x. And then I have positive 2 times cosine of x plus 2 cosine of x. And then I have plus or minus cosine of x times 0. So it would be the antiderivative of 0, which is just 0. So I don't really write that one down. That's just my check to make sure that I'm finished. So I really just need to write down that I'm adding a constant because I'm finding an antiderivative. And that is integration by parts. Now, when you look at your chart, that's how many integration by parts I would have to do. So if I was doing this using the old style, then I would be doing 1, 2, 3 separate integration by parts before I got my final answer. So let's look at example 5. This is a different style. I'm going to use the same technique, but we're going to stop when we multiply across gives you a form of the original integral. So when I multiply across, I'm looking for e to the x times sine of x. So I have a u, I have a dv, I have to figure out which is which. E is e, sine is trig, so I'm going to use trig as my u. So my u is going to be sine of x, and my dv is going to be e to the x. So in this one, if you look at your u and you start taking your derivative, I'm never going to get to 0. My derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of negative sine is negative cosine. And that's just going to continue to repeat, which is why in this, and same with my dv, the antiderivative of e to the x is e to the x. So I have to continuously look across to see when I get to the same situation that I'm in right now, which is when I multiply across, I get e to the x times sine of x. So I'm going to take I'm going to take the derivative of u to start. The derivative of sine of x is cosine of x, and then I'm going to immediately take my dv, which is e to the x. When I multiply across, that's not the same thing as what I started with. So I do it again. The derivative of cosine is negative sine of x, and the antiderivative of e to the x is e to the x. When I multiply across, that would be negative sine of x times e to the x. I get a form of e to the x times sine of x. I just have a constant in there, my negative. So I don't care about the constants. I simply care about the terms that I have there. So I'm continuously checking. I'm finished here. Now I'm going to go ahead and put in the plus and minuses. I always start with a plus on the first term, a negative, and a plus. And then I'm going to multiply diagonally. And then I'm going to go across is my antiderivative. So let's write this out. The antiderivative of e to the x sine of x dx is equal to e to the x sine x, that's my first diagonal line, minus e to the x cosine of x. Sorry, I'm going to go below. And then I have minus the antiderivative of e to the x sine of x. Technically, there's a dx there. So for that last one, multiplying across, that is the antiderivative. Now, this is like that last one we did where we had an a basically on both sides of our equation. So I'm going to add the integral of e to the x sine of x to both sides. And what I end up with is the antiderivative of two antiderivatives of e to the x sine of x dx is equal to e to the x sine of x minus e to the x cosine of x, and I divide both sides by 2. So the antiderivative of e to the x sine of x dx is equal to e to the x sine x minus e to the x cosine of x, all divided by 2. And don't forget that this is an antiderivative, and add your plus c. So there we have an integration by parts where we end up with the same thing we started with, not counting the constants. Moving on to example 6. So this is the last style that we have, and this is when we have to steal. I don't know another way to say that. So we start with a u and a dv, just like we always do. In this case, I have x to the fifth is algebraic, and then e to the x squared is e, and of course a comes before e and ilate, so my u is x to the fifth. My dv is going to be what I have left over, which is e to the x squared. Now, here's the problem. I can take that derivative and I can get it to go down to 0, no problem. Where my issue is with my dv. I have to be able to take the antiderivative of e to the x squared. I can't unless I have the derivative of the inside. Now, the derivative of the inside is an x. So, what happens is we can't integrate it as it stands. So we can't integrate e to the x squared without an x e to the x squared for the derivative of the inside. Now, that's not the whole derivative of the inside, but I can deal with the 2 on my own because it's a constant, which means, which means I need to steal. So I'm going to steal an x from my u. So just a little side note, don't write this down. X to the fifth is the same as x to the fourth times x to the first. So I'm going to take this x to the first and I'm going to put it with my dv. So my x is going to go over here, which leaves me with an x to the fourth on this side. So I still have this e to the x squared over here. That's an x squared. So I haven't changed what I have when you multiply across. That's the key. When you multiply across, I still have x to the fifth e to the x squared. But I did make a little bit of a change. So I need to put a little dashed line in here to kind of indicate I didn't actually use that top line at all. I had to rewrite it before I could use it. And now we're going to do our derivative of our u and our antiderivative of dv. So the derivative of our u is 4x cubed. The antiderivative of what we have over here is still e to the x squared, but I need a 2 really for the derivative of the inside is 2x, which means out here I'm going to need a 1/2. So I take a look at my u, I can happily take that derivative. I look at my dv, I cannot take that derivative, which means I need to steal again. So I'm going to dash some lines saying I'm not really using that line. What I'm really going to do is I'm going to have a 4x squared here, and I'm going to bring an x to the other side. So I have a 1/2 x e to the x squared. Now I'm prepared to take my derivative, which is 8x, and I'm also prepared to take the antiderivative. Again, the derivative of the inside is 2x. My 1/2 is going to stay along for the ride. My x is already there. I need a 2 for the derivative of the inside, which means I really need a 1/2 on the outside. And I'm sure we can translate that as really 1/4 in front of the e to the x squared. So again, I can't take this antiderivative, so I've got to steal one more time. So this is actually just going to be an 8. And over here, I'm going to have a 1/4 x e to the x squared. So take my derivative of 8. That gives me 0. I'm happy. That's where I wanted to end. I take the antiderivative of this, and this is going to be a 1/8 e to the x squared. Again, the derivative of the inside is 2x, so I need to add to multiply by a 1/2. So I'm not going to use this line. This is my plus. Now, I didn't actually use the next line. I used the one after the dashed line, and then I didn't actually use the next line. I used the one after the dashed line. So these are the ones that I actually used. So now I'm going to multiply across. And when I multiply across, we never cross the dotted line. Never cross the when you're multiplying. Diagonally. Okay, so here we are. We now have the integral of x to the fifth e to the x squared dx is going to be 1/2 x to the fourth e to the x squared minus x squared e to the x squared plus e to the x squared plus c. I did some simplifying in my head when I was multiplying, so give that a second. You can go ahead and pause the video if you didn't follow where those came from. Moving on to the last example. We have the same situation. We're going to be stealing again. So we need a u and a dv. And I need to select my u. And what I have is I have an algebraic for the x to the seventh, and I have a natural log for my ln, and using ILATE, L comes first. So the natural log is actually my u. So my u is going to be ln of 3x. And that means that my dv is going to be x to the seventh. So at this point, I'm going to go along my merry little way, and I can find this antiderivative x to the seventh. I can find that easily. I can find my derivative easily as well. So I have 1 over 3x times the derivative of the inside, which is 3. And of course, that's going to simplify just to 1 over x. My antiderivative is going to be x to the 8th divided by 8. And again, I can find that antiderivative all day long. That's an easy one. But what I'm noticing is, let's just take a little side trip over here. If I have 1 over x, that's the same as x raised to the negative 1. When I take that derivative, I get negative x to the negative 2. When I take that derivative, I get 2x to the negative 3. When I take that derivative, I get negative 6x to the negative 4. Do you see what's wrong? This is never, ever, ever going to get to 0. It's never going to get to 0. Not going to happen. Which means I need to do some stealing again, because my derivative is never going to get to 0. So my derivative never gets to be 0. So we're going to steal again. And it's the same process. We're going to put a little dashed line to indicate I'm not exactly using what's right there. I'm going to steal first. And this really is a 3 over 3x, which is 1 over x. So if I take out a 1 over x, basically, that leaves me with just a 1. So what I'm taking out is a 1 over x. And when I take that out, I'm going to multiply that to my dv. So my dv is then not going to be x to the 8 anymore. It's going to be x to the 7th. But I still have my divided by 8. So I take my derivative of my u, which gives me a 0, which makes me very happy. My antiderivative here becomes x to the 8th divided by 8. So on the bottom I have 8 times 8, which is 64. And from here, I'm going to put in my plus sign to the first term I'm going to use. I did not use the second set, so the negative sign goes with the next one. And I'm going to have the antiderivative of x to the 7th natural log of 3x dx is equal to 1 over 8 x to the 8 natural log of 3x minus x to the 8 over 64 plus a constant. So here is my antiderivative. I apologize for the length of this video if you watched it all at once, but regardless, I think you should be good with integration by parts when we work on that in class, and I hope you have a wonderful evening.